The moon. Pretty cool that we have a huge chunk of igneous rock just floating in the sky. I mean, I know it's not like floating in the sky. I get how gravity and space work, but like, you know what I mean. By the way, people always say there's a man in the moon. I do not see it. Um, I mean, could these be the eyes and the mouth? I don't really know. Or is this like a big smile and then nose, eyes? I don't know. I don't see it. But anyway, what is the moon and where did it come from? So this should be reviewed since we learned this in Earth history, but just as a recap, the moon used to be a planet called Theia, and this was during a time when there were hundreds of planets in our early solar system, about 4.5 billion years ago, and Theia crashed into Earth, or there was a collision between the two bodies, and that was a really violent event, and they both melted. The planet Earth and Theia melted. Earth, being the bigger body, kind of pulled the material that was Theia into orbit, and now it's cooled off, and we call it the moon. And it's the reason that Earth is tilted on its axis from that violent collision. And the moon's also famously the only other place that we've ever been besides Earth in the universe. And as a quick tangent, just because I know there's a lot of people that actually don't even believe in the moon landing, but we definitely landed on the moon. There's lots of evidence. The strongest evidence is, of course, that the lunar landers are still all on the moon, and our satellites can see pictures of them. I know it's hard to see, but that's Apollo 11 right there, which was the first manned mission to the moon. We've got really detailed photos of Apollo 12, which was the next manned mission. And we've got very detailed photos of a lot of the other missions too. This is Apollo 12, which also brought people, and Apollo 14. So all of the lunar landers are still on the moon, and we can see them with our satellites. This is a detailed photo of the Apollo 14 landing site. And here's another detailed photo, this time the Apollo 17 landing site. So we can see a lot of the equipment that brought us to the moon is still actually on the moon. Even our footprints are on the moon, and we can see that stuff in our satellite pictures. There's also thousands of photos of people hanging out on the moon, and honestly, it looked like a pretty good time. They were riding around in buggies, posing patriotically by the flag, and Alan Shepard even shot 2 golf balls, which is kind of a cool story. He didn't tell a lot of people before he went up there, busted out the golf club, and hit 2 balls. The first one he shanked to the side, but the second one apparently went for a couple miles. So that was pretty cool. So I'm sure you've noticed that it looks like the moon changes shape every night, and that'll be the focus of our lesson today, why this happens. So like we said, it looks like the moon changes shape every night, and we call those different shapes phases. So today's lesson will be all about interpreting from diagrams what phase could be seen from the Earth. And as we'll learn, it's all about the relationship between the sun, the moon, the Earth. Primarily that the moon is in orbit around us on Earth, and the Earth is also in orbit around the sun. So the foundational point today, or the most important thing, is that the moon revolves around the Earth while the Earth revolves around the sun. And the interaction between the Earth, the sun, and the moon contribute to the phases of the moon and how they change. And interestingly, for the entire history of humanity, we've only ever seen one side of the moon from Earth. So we always see the same side of the moon from Earth because the period of rotation and the period of revolution for the moon are the same. The moon takes 27.3 days to rotate, and it takes 27.3 days to revolve around the Earth. That means that as the moon is revolving around the Earth, every day it rotates or it spins just enough to face the same side of the Earth. And it's no coincidence, but this happens when a smaller body orbits a larger body. Over time, the gravitational interaction between the two causes the rotation of the moon to slow down. So it kind of matched up, and now the same side of the moon always faces the Earth as the moon revolves. Now, even though that number is 27.3 for the revolution, the cycle or the phase of different shapes takes 29.5 days to repeat itself. So about a month. And the reason for these extra 2 days is that as the moon revolves around the Earth, which takes 27.3 days, the Earth is still in motion. The Earth is moving around the sun. So 27.3 days goes by and the Earth has changed its position. So it takes 2 extra days for the moon to catch up to where the Earth was. So let's dig into these phases and figure out why they happen and interpret the diagram so we can figure out what phases we can see from Earth. So let's start with the full moon. That's like the most famous moon phase. It's when the moon is fully illuminated and you can see the entire circle of the moon in brightness. And if we look at the orbit, we see that the full moon is right here. So why is the full moon in this position but not the other ones on this diagram? Well, every time I'm interpreting these diagrams, I always want to block out the back side of the moon. That means the side of the moon that I'm not going to see from Earth. And I'm going to use this rectangle, but if you had your own diagram, you could just use your hand to block out the backside or put your thumb over the backside. And what I do is I imagine if I'm on Earth in this diagram and I'm looking at this side of the sun, or this side of the moon, sorry, what am I going to see? Well, obviously I'm only going to see the side that's facing Earth. I'm not going to see this back side of the moon, so that's why I covered up the backside. So if I'm on Earth and I'm looking up at the moon and I know that the moon is a three-dimensional object, or close to a sphere, it's not like a flat piece of paper, or a computer screen, which is what we're looking at. I know that everything that's not blocked out here is illuminated, and that's a full moon. That means I'm going to see everything. I blocked out all the shading, so in this part of the diagram, I'm going to see the full illumination of the moon. Next, we'll jump to the opposite side of the diagram, and that's the new moon. So again, I'm going to block out the side of the moon that's not facing Earth, and then my job is to imagine what it's going to look like if I'm an observer here on Earth looking up at that moon. Well, in this part of the diagram, because the sun's over here, the part that I'm not going to see from Earth is illuminated, but the part that I do see from Earth is fully blacked out. So a new moon looks like nothing in the sky. The moon is still there, but we're only seeing the shaded part of the moon, so it looks like there's nothing in the sky. It's just a fully shadowed moon because the bright side of the sun is over here, but that's the side that's facing away from Earth, so we don't even see that side. We only see the shaded side. So a new moon looks like nothing. I'm going to jump around a little bit here, but again, I wanted to start with those two easier ones, the full moon and the new moon, because they're kind of easier to visualize. But now we're going to go back to the full moon, and we're going to go this way in the order of the revolution and compare them to what we see down here from Earth. So we talked about the full moon, right? We only see the illuminated side from Earth, and so we see everything. And next is going to be the waning gibbous. So let's look at this part first. A waning gibbous, waning meaning the light is going away. It's a little sliver of darkness on the right side and mostly illuminated on the left side. So again, we can use the same strategy. We can block out everything that's not visible from the Earth. So I've blocked out the back side of the moon, and I'm thinking about what I can see from Earth. And, well, it kind of matches up to this. It's a little bit of shading on the right side, like right here, and mostly illuminated on the left side, which is consistent with the picture down here. And because we know that the moon is a 3D object, so we have to imagine the full circle, but the rules of the lighting still apply. We got mostly light on the left and a little bit of darkness on the right, and again, mostly light on the left and a little darkness on the right. All right, now that we get the basic procedure, we can move through the rest of these a little quicker. So the first step is always to block out the back side of the moon, and that's the side we don't see from Earth. And imagine that I'm on the Earth looking at this moon here, and it's half and half with the brightness on the left side. So that matches up here with our third quarter, half and half, and the brightness being on the left side. Waning crescent, same thing. Block off the backside. Whoops. Block the backside of the moon. And imagine what it looks like. This time, just a sliver of brightness on the left with mostly darkness. And that matches here. A little sliver of light on the left and mostly darkness on the right. Talked about the new moon. Blank. From Earth. It's still there, but we're just seeing the shadow. Now we get to the lower side of the diagram, and it's kind of tricky. I'll show you two ways. So first, same way we've done. You block the backside of the moon. I'm on the Earth here, and I'm looking at this moon, and the brightness is on the right side. And I'll show you in a second when we flip it, but here I'm on the lower side of the Earth in this diagram, so the brightness will actually be on the right side of the moon, which is why the waxing crescent has brightness on the right with mostly darkness on the left. So another way to test these lower ones on the diagram is to just flip the image so that it's no longer reversed. This is one case where a paper packet might be a little better because you could just flip your paper. But if you have your phone, maybe you could flip your phone over, or I'm rotating the screen now, so we'll just go with what I'm looking at now. So we'll do the waxing crescent again. We said the brightness was on the right side because in this diagram, when I was on the bottom part of Earth, I look up here and the brightness is on the right, which is why when I flip it back for the waxing crescent, the brightness is on the right side. Okay? Now checking our first quarter, block off the backside. We're looking at it from Earth. We're imagining, okay, we know it's half and half, but because of this whole flip factor, because this is the bottom part of the diagram, that's actually going to be on the right side, not the left side, even though it looks left. So I'll look down here at the picture. Oh, okay. So the first quarter is illuminated on the right side. And again, we have the flip test. So looking at this, oh, okay, so the brightness is on the right side because if I was on Earth here, this is how I would see that moon, with the brightness being on the right. And finally, our waxing gibbous will block it off from the back, and we got the illumination, or the brightness, being on the right side because of the flip test, and a little bit of darkness on the left. And here we go, waxing gibbous, mostly brightness on the right, and a little bit of darkness on the left. So there we have it, the phases of the moon, why they occur, and how we can interpret them. And I'll talk to you guys next time.